Hi, my name is Ziyi Wang, and I'm presenting our work on Variational Inference MPC using Tsallis Divergence. In this work, we extend the Variational Inference MPC framework using the more general Tsallis Divergence and explore the connection of the framework to other sampling-based stochastic optimal control algorithms. And finally, we provide theoretical and numerical risk sensitivity analysis of the framework. First, let's look at the standard VI MPC setup. We can view the stochastic optimal control problem as an inference problem by introducing a dummy optimality variable. And then now the objective is to just sample from the optimal posterior distribution of the trajectory. However, we can't directly sample from the posterior optimal distribution. So instead, we need to minimize the distance between the control distribution and then the target optimal distribution. And through some reformulation, we get to the following two terms, with the first term being the negative log likelihood function of the optimality, and the second term is the KL divergence between the control distribution and the prior distribution, which act as a regularizer. The optimality likelihood can be parameterized by any non-increasing function of the trajectory cost, such that higher costs always correspond to lower optimality likelihood. And then common choices of the function are negative exponential and indicator function. And here we choose the negative exponential function. And note that we can also interpret the problem formulation above as an application of the maximum entropy principle using Shannon entropy. And in our work, instead of using the KL divergence, we now use a more general Tsallis divergence as a regularizer. But first, we need to define the deformed log and exponential functions, which generalizes the standard log and exponential functions. And we can recover the original definitions by taking R to 1. And now we can use those to define the Tsallis entropy and divergence accordingly. And note that we can also recover the original Shannon entropy and KL divergence by taking R to 1. Now we can replace the KL divergence from earlier with Tsallis divergence, and then we can solve for the optimal distribution Q star explicitly and obtain a closed form solution. And using this, we can obtain the distributional policy update law for different policy distributions, such as a unimodal Gaussian, a mixture of Gaussian, and Stein particles. We also compare the VI MPC framework against other popular sampling-based stochastic optimal control algorithms like stochastic search, MPPI, and cross-entropy. From the cost function, objective function, we can see that MPPI can be achieved from the VI framework by choosing the negative exponential as the optimality likelihood function. And then the update laws of the KL VI, Tsallis VI, MPPI, and cross-entropy can all be recovered from the stochastic search update law through the appropriate choice of the shape function S. We have also introduced a reparameterization of the framework to make the algorithm more interpretable. And then the newly introduced parameter gamma now defines a cutoff threshold similar to cross-entropy method. And then from the bottom left plot here, we can see that we can recover the cross-entropy method by taking R to infinity, and we can recover the MPPI method by taking gamma to infinity and choosing R appropriately. Finally, we perform a risk sensitivity analysis through the absolute risk aversion coefficient, which characterizes the ratio of the mean and the variance of the Taylor series expansion of the objective function. And then a positive coefficient here corresponds to risk-seeking behavior, and the negative coefficient corresponds to risk-sensitive behavior. And then here we can see that MPPI always has a positive coefficient, so it's always risk-seeking. And then for the cross-entropy method, when the cost is below the threshold, the coefficient is negative infinity, so it's infinitely risk-sensitive. But for the Tsallis framework, we can choose to go between risk-sensitive behavior and risk-seeking behavior through appropriate choices of R. We have applied the framework and then to various different problems, starting with a static optimization problem with noisy objective evaluations. And from the plot here, we can see that the Tsallis framework achieves a solution that's the closest to the global minimum. We have also applied these frameworks on different problems in simulation. And then from this table here, we observe that the Tsallis framework outperforms MPPI and cross-entropy for all different policy distributions in terms of the mean cost. And then it beats them in many cases for the standard deviation, and then only losing out in very few scenarios. Thank you so much.